Hello everyone, my name is Jiajun Ma. I came from the University of Strathclyde in the Department of Electronic and Electrical Engineering. My research topic is for stochastic power flow calculation in distribution network based on the point estimation method, comparison with the Monte Carlo algorithm. In this presentation, I will from 7 aspects to introduce my research based on the research background and the current research situation and the research gap. I propose my research method and I will give you a simulation model and a case study. From that, we can get the result and get a deeply analyze. Deterministic power flow calculations assume that the system parameter like load, generator output are constant, providing a single point solution. However, in real-world systems experience fluctuation due to various demand and external distribution. This limitation prevents deterministic method from currently modeling the dynamic nature of modern power grid, particularly with the increasing integration of variable renewable energy source. The renewable energy sources like the wind, solar are variable and unpredictable due to it depends on the weather condition. This fluctuation introduces randomness into grid, affecting key operation parameters such as the voltage, current, and the power flow. As renewable penetration increases, this issue becomes more pronounced. Necessitating method can accommodate such variability. The stochastic analysis accounts for probabilistic nature of power system variables, providing a more comprehensive understanding of grid behaviors. Instead of a single point result, the stochastic method produces a range of possible outcomes, which associates probabilistic helping operator and planning for the uncertain things. This approach is particularly valuable for identifying the weak point in the system and assess the impact of the renewable energy integration on network stability and reliability. By addressing variabilities and randomness, the stochastic power flow analysis enables the design of more efficient power system. The Monte Carlo method involves rapid random sampling to compute the probabilistic distribution of the power flow parameters. It provides highly accurate results by simulating a wide range of input variabilities and generating corresponding outcomes. However, this method is computationally intensive, requiring thousands, even tens of thousands of iterations to achieve reliable results. The high computational cost is make impractical for real-time applications and other large-scale of power systems. The convolution method calculates the probabilistic distribution of output variables by integrating the distribution of the input variables. While it is straightforward, it becomes inefficient when applied to systems with numerous variables and complex load distribution. With the increasing penetration of the renewable energy source, this is a growing demand of methods that can balance accuracy and computational efficiency. Such method allows for real-time grid analysis, enabling the system operator to adapt the dynamic grid condition while maintaining the stability and the reliability. As for the research gap, the first one is computational intensity of Monte Carlo simulations. The second one is the limited applicability of convolution for fluctuating renewable energy. So it needs for efficient and reliable stochastic analysis method. The three-point estimation method provides an efficient approach to calculating statistic power flow by estimating key statistical moment of input variables. It reduces computational complexity by using three strategical choosing points to approximate the distribution of each input variables. These 3 points typically representing the mean and the two deviations enable current estimation of output parameters without the need of exhaustive sampling as required in the Monte Carlo simulations. The Native transformation is employed to handle correlations between the input variables such as the load demand and the renewable energy output. This transformation converts correlated random variables into a set of independent standard normal variables, simply the analysis. By considering the variables' correlations, this method improves the accuracy of the stochastic modeling, reflecting realistic system behaviors more efficiently. The combined approach of three-point estimation and native transformation keep a balance between the computational efficiency and the result accuracy. Unlike the traditional method, this methodology significantly reduces the computational effort while providing results comparable to Monte Carlo simulations. This efficiency makes it suitable for real-time applications and large-scale power system analysis. The IEEE 33 bus test system is used to validate the proposed stochastic power flow model for distribution network based on the three-point estimation method. The topology of the node is shown in this figure. This is a radial distribution system, has a base voltage of 12.66 kV and a base power of 100 megawatts. Bus 1 is served as a slack bus with a voltage of 1 point per unit, and the standard deviation of the load fluctuation each bus is set to 30%. This system includes 32 branches. The parameters of the test system are taken from the standard IEEE test system specification. To assess the efficiencies of proposed algorithm, compare is made with the result obtained from 10,000 Monte Carlo simulations. The parameters of photovoltaic panels and the wind turbines are presented in these two tables, respectively, and the distribution energy sources are tested as PQ nodes, with their output considered as negative power loss value. The figure gives a comparison analysis of expected value of node voltages, branch active power, and the branch reactive power calculated by using three-point estimation method and the Monte Carlo method. Reveal that the result curve from both algorithms coincide, indicating minimal calculation error. After integration distribution generation, the voltage magnitude at node 18 and node 33 shows a significant increase. As for the branch 17 and branch 33, the expected value of both active and reactive power are negative due to low load and at the end, and the integration of wind and photovoltaic power result in the reverse flow of the active and reactive power back into the system. These three figures show that the curve produced by both algorithms overlap, indicating that the calculation difference is minimal. Following the integration of distribution generation and the voltage magnitude at node 18 and node 33 significant increase, branch 17 and branch 33 shows a negative expected value for both active and reactive power caused by the low load at the branch end and the addition of the wind and the photovoltaic power source result in the reverse power flow both active and reactive back into the system. These two slides show the same results. These four diagrams illustrate the probabilistic distribution of voltages at node 18 and node 33, as well as the probabilistic distribution of active power for branch 17 and branch 33 respectively. In the two diagrams on the left, the voltages at node 18 is slightly higher than that at node 33, which represents the system's lowest voltage point. The standard deviation of the voltage fluctuation at node 18 and node 33, indicating relatively large fluctuation at the node 33. In the two diagrams on the right show that the expected active power value for branch 17 and 33. This indicates a reverse power flow occurring at these nodes due to the integration of the wind power. The standard deviation of active power fluctuation are 0.005 per unit for branch 17 and 0.0012 per unit for branch 33, with the branch 33 shows the relatively large power fluctuation. So the three-point estimation method has been demonstrated to provide the results with accuracy comparable with Monte Carlo simulation. By significantly reducing the computation time, this method addresses the limitation of the computational intensity in traditional stochastic method. This method efficiently computing the probabilistic nature of power flow parameters, including the variation due to the renewable energy source and the load demand. The capability ensures a better representation of the real-world operation condition in distribution network. The three-point estimation method facilitates the integration of renewable energy by accounting for its inherent variability and randomness. It enables grid operator to manage renewable penetration efficiently while maintaining the system's stability and reliability. The method is well suited for modern power systems where computational efficiency and current are critical. It offers a practical tool to optimizing the grid performance and supporting the transition to sustainable energy system. That's all of my presentation. Thanks for your listening.